A star nearly 1,700 times wider than our Sun is breathing in the constellation Scutum. A different team, using different instruments, says that same star is closer to 900 solar radii and may not even rank among the top 5 giants we have ever measured. Both numbers come from real telescopes. Both come from careful teams who checked their math, published their methods, and stood behind what they found. And yet the two figures describe the same object, sitting in the same patch of sky, roughly 10,000 light-years from where you are right now. That gap is not a rounding error. It is the difference between the largest star humans have ever catalogued and a star that is merely enormous, and the answer has real stakes for how we think about stellar death, about how giants like this end their lives, and about whether our sense of scale in the universe has an upper limit we have actually found yet. The star at the center of this story is called UY Scuti. It was found by accident, ignored for almost a century, and then measured, twice, by 2 generations of astronomers who came back with wildly different answers. To understand why, we have to start where they started. Chapter 1. The year was 1860. A team of German astronomers in the city of Bonn was in the middle of a project that had never been attempted at that scale before. They were trying to catalog every star visible from their observatory, one entry at a time, working through the sky in careful strips, night after night, by the light of oil lamps and candles. They were not hunting for anything spectacular. They were counting, recording positions, writing coordinates into leather-bound notebooks with the patience of clerks. The romance we now attach to astronomy was, for them, mostly bookkeeping, and their bookkeeping happened to sweep through a crowded region of the Milky Way called Scutum, the shield, tucked near the summer band of the galactic plane. In one of those strips of sky, they logged a faint reddish point of light. They assigned it a number. They moved on to the next star, and the next after that. Nobody in the room understood what they had just written down, because at that moment there was no reason to understand it. The dot looked ordinary. It behaved, on that first pass, like anything else in the catalog. The strange part came later. On a second sweep, through the same region, one of the astronomers noticed that the dot did not match its earlier entry. Its brightness had shifted. That should not happen. Stars are supposed to be the steadiest objects a person can point at. They hold their light for centuries, for millennia, for as long as human record-keeping has bothered to check. A star that flickers is a star that is doing something. That single anomaly earned the object a new label. It became a variable star, a member of a small and unusual group whose brightness rises and falls on cycles that early astronomers could measure but not yet explain. It received a designation that would stay with it for the rest of its documented history, UY Scuti, and then it sat quietly in the catalog for almost a century, useful mainly as a footnote for anyone studying the Shield constellation in detail. It was not until 1979 that anyone pointed serious instruments at that faint red dot and asked what it actually was. When they did, the numbers that came back did not fit anything the researchers expected. They ran the calculations. They ran them again. They checked the distance estimates, the brightness measurements, the assumptions about how much interstellar dust sat between Earth and the star. Every check they performed made the answer more difficult to swallow, not less. The radius of UY Scuti, the distance from its center to whatever counted as its outer edge, was so large that ordinary comparisons stopped working. To describe it, the researchers had to abandon the usual language of astronomy and reach for something visceral. Start with what you already know. Our sun is not a small object. More than 1 million Earths would fit inside it. If you could somehow drive a car across the sun at highway speed, the trip from one side to the other would take you about 200 years. Longer than any human lifespan, longer than the United States has existed as a country. That is our ordinary, comfortable, middle-of-the-road star. UY Scuti, at the upper end of its estimated radius, is roughly 1,000 times wider than that. If you placed it where our sun currently sits, its surface would not stop at Mercury. It would not stop at Venus. It would sweep past Earth without noticing, past Mars, past the asteroid belt, and reach somewhere near the orbit of Jupiter before its outer atmosphere finally faded into space. Every planet that any human being has ever walked on, dreamed about, or launched a probe toward would be inside the body of this one star. And yet, from where we are standing, it is almost impossible to see. UY Scuti sits roughly 10,000 light-years away. tucked behind thick lanes of interstellar dust that dim its light before it ever reaches our telescopes. To the naked eye, on a perfect night, in a perfectly dark location, you would not find it. You would need a telescope. You would need someone to point you at exactly the right patch of Scutum. You would need to know what you were looking at, because what you would see would not look impressive. It would look like a faint reddish smudge. That contrast is worth sitting with. The most extreme object in our stellar neighborhood, possibly the largest single star humans have ever measured, hides so effectively that most people who have looked at Scutum through a backyard telescope have looked directly at it without knowing. But this is where the trouble in our story begins. Because the moment researchers tried to pin down exactly how large UY Scuti is, they discovered that the question itself was harder than it looked. A star should have an edge, something you can point to and say, here is where the star stops and space begins. Red hypergiants like UY Scuti do not offer that courtesy. Their outer layers do not end. They fade. Plasma and gas thin out gradually with distance, like a fog bank that gets slowly less dense as you walk away from its center, until at some point you are no longer inside the fog, but you cannot say precisely when you left it. The surface of UY Scuti behaves the same way. Different instruments, tuned to different wavelengths of light, actually see different sizes for the star, because each wavelength escapes from a different depth inside that fuzzy outer region. This is not a philosophical quibble, it is a measurement problem with real numerical consequences. One team, using one method, might measure the star at a certain wavelength and report a radius. Another team, using a different wavelength and a different method, might measure the same star at the same moment and report a radius that differs by hundreds of solar radii. Not because either team made a mistake, but because they were, in a real sense, looking at different layers of the same object. Layered on top of that is a second complication. UY Scuti is wrapped in a thick envelope of dust that the star itself has produced. Over millions of years, gas has poured off its surface, drifted outward, cooled, and condensed into tiny particles that now form a shell around the entire star. That shell blocks visible light almost completely. To see UY Scuti at all, astronomers have to use infrared telescopes that can peer through the haze, and infrared measurements carry their own set of uncertainties, their own assumptions about how the dust behaves, their own margins of error, and the star itself is not sitting still. UY Scuti pulses. It expands and contracts on a cycle of roughly 740 days, which means the radius you measure today is not the radius you would measure a year from now. Pinning down the size of an object like this is a little like trying to measure the height of someone who is jumping. The number you get depends entirely on when you decide to look. The larger number came first, and it came from a body of work that stretched across the late 1990s and into the early 2000s. Infrared surveys were finally becoming powerful enough to study red hypergiants systematically rather than one at a time. Teams working out of institutions in Europe and the United States began turning those instruments toward the Scutum region, and when they modeled the light coming back from UY Scuti, the numbers they extracted pointed toward a genuinely extreme object. The reasoning behind the 1700 figure was not a single measurement. It was a chain, and each link in that chain was defensible on its own terms. The first link was luminosity. When astronomers add up all the energy an object is radiating across every wavelength they can detect, they get a total that describes how much light the star is producing, in absolute terms, regardless of how far away it happens to be. For UY Scuti, that total came out staggering. The star appeared to be pouring out something like 300,000 times the energy of our sun, every second, without pause. That number by itself does not tell you how large a star is, but it sets a constraint. Physicists have known for more than a century that the energy a star radiates depends on two things: its surface temperature and its surface area. If you can measure the temperature, and you know the luminosity, the surface area follows from a straightforward equation that has been sitting in astrophysics textbooks since the 1800s. UY Scuti's surface temperature, judged from the shape of its spectrum, sits around 3200 Kelvin. That is genuinely cool for a star. Our sun, by comparison, runs at roughly 5800. The moment you plug a low surface temperature into the equation alongside an enormous luminosity, the math forces the surface area to be extraordinary. Because a cool surface radiates less energy per square meter, so you need vastly more square meters to reach the total the observations demanded. Run that calculation with the numbers the infrared surveys were reporting, and the radius comes out somewhere near 1700 solar radii. Not because anyone wanted the answer to be that large, but because the physics did not leave much room to arrive anywhere else. The luminosity was what it was. The temperature was what it was. The equation had been trusted for over a century, and the star it described was, on those numbers, one of the largest objects that had ever been catalogued. The camp that built its position around this figure was not naive about the difficulties. They knew about the dust envelope. They knew about the pulsation. They knew that the star's outer atmosphere faded into space rather than terminating cleanly. Their argument was that all of those complications were already folded into the luminosity measurement because the infrared observations captured the star's total energy output, whether that energy was coming from a sharp surface or a diffuse one. Energy is energy. The star was radiating what it was radiating, and if the radiation was that intense at that temperature, the emitting surface had to be that large. There is a second thread of reasoning worth taking seriously here. The dust shell around UY Scuti is enormous. It extends, by some estimates, out to nearly 400 times the distance between Earth and our Sun. That envelope did not appear from nowhere. It was blown off the star, layer by layer, over hundreds of thousands of years. A star that has produced a dust shell of that size must have been shedding mass at an extraordinary rate for an extraordinary length of time, which in turn implies that the star itself has been operating at extraordinary luminosities for most of its life. The size of the envelope backs up the size of the star that made it. Those two numbers reinforce each other, and that mutual support was part of why the 1700 figure held in the textbooks for as long as it did. There is also a temperament question in this story that deserves acknowledgement. The camp that argued for the larger radius was, in many cases, working at the frontier of what infrared instrumentation could do at the time. They were making the best measurements available with the best tools available, and they were doing so with full awareness that future instruments might refine their answers. They were not staking a claim on the number 1700 as final truth. They were reporting what the data, at that moment in that decade, most naturally implied. That is how careful science actually works. It publishes what the evidence supports and waits for the next generation of instruments to test it. But there is a genuine counter-reading that lives inside this same chapter, and it is worth putting on the table now, because the 1700 camp itself acknowledged it as a real possibility. The dust envelope that surrounds UY Scuti glows in the infrared. When dust absorbs light from the star and warms up, it re-radiates that energy at infrared wavelengths, which are precisely the wavelengths the surveys were using to measure the star in the first place. That creates a genuine ambiguity. When an infrared telescope points at UY Scuti and records a certain amount of energy, some of that energy is coming from the star's true surface, some of it is coming from the inner edge of the dust envelope, and some of it is coming from warm dust that sits farther out still. Distinguishing those contributions requires models, assumptions about how the dust is distributed, how it absorbs and re-emits light, how much of the total signal belongs to the star itself versus its cocoon. The alternative case did not arrive as a dramatic overturning. It arrived slowly, through a different generation of instruments and a different way of asking the question, and its supporters would argue that they were not shrinking the star so much as measuring it more honestly for the first time. The core insight behind the smaller number is deceptively simple. When you look at a red hypergiant, you are not looking at a solid ball with a well-defined skin. You are looking through a graded atmosphere, and every wavelength of light you choose to observe reaches down to a different depth before it becomes visible to your instrument. Short wavelength light gets absorbed by the upper layers and only escapes from near the top. Longer wavelengths slip past those upper layers and only become detectable from deeper, warmer regions of the star. That difference is not a small technicality. It has real numerical weight. If one telescope, working at one set of wavelengths, is effectively seeing the outermost fringes of the star, and another telescope, working at different wavelengths, is seeing hundreds of solar radii deeper, those two instruments will report very different sizes for the same object, and both will be correct within the terms of their own measurement. The camp that arrived at the smaller radius argued that the earlier surveys had, in effect, been measuring the outer skirt of UY Scuti rather than the star's true body. The 1700 figure, in their reading, captured a region where the star's material had already thinned, to something more like a slow, glowing wind than an actual stellar surface. Push past that thinning region, look for where the density and temperature transition into what a star physically is, and the object they saw was closer to 900 solar radii across. There is a physical argument behind this framing that goes beyond wavelength alone. Red hypergiants are held together loosely at their outer edges. Their gravity, out at those enormous distances, has weakened so much that material barely stays gravitationally bound to the star at all. Some of what an infrared survey picks up in the outer layers is, in a strict sense, no longer part of the star. It is material on its way to becoming part of the interstellar medium. Treating it as stellar surface, in this reading, inflates the measurement in a way that does not reflect the underlying object. The teams working with this interpretation also pointed to something else that the earlier figure had trouble accommodating cleanly: stellar evolution models. The equations that describe how stars of different masses live and die do not comfortably produce objects with radii much larger than about 1,500 solar radii. A star that large tends to fall apart. Its outer layers are so weakly held that even modest perturbations can strip material off in bulk, which prevents the star from staying that large for long. That is not a hard ceiling, but it is a strong statistical expectation. When observations returned radii near 1,700 solar radii, the smaller camp researchers noted a tension between what was being reported and what evolutionary models would predict. Either the star was an outlier of unusual proportions, or the measurement was picking up more than the star itself. A revised figure near 900 solar radii sat much more comfortably within the range that stellar physics expected for an object with UY Scuti's mass and age. There is also a second physical thread here. The camp arguing for the smaller radius used their measurements to work backward toward a mass estimate for UY Scuti, and the mass they arrived at was substantially lower than what a genuine 1,700 solar radii giant would need to hold itself together. In their view, a star with UY Scuti's mass simply cannot maintain a stable radius of 1,700 solar radii for any meaningful stretch of time. Something has to give. Either the mass estimate is wrong, or the radius estimate is wrong, and their reading of the data suggested that the radius was the more likely candidate for revision. None of this made the smaller number a comfortable conclusion for everyone, because the same wavelength dependence that supports it also cuts the other way. If different wavelengths reach different depths, then it is at least possible that the instruments returning the smaller radius are penetrating too far into the star, missing genuine outer structure that longer wavelength observations would have captured. In that reading, 900 solar radii is not the star's true edge either. It is the point at which the observing wavelengths finally stop before they would have gone deeper still. The smaller camp researchers acknowledged that possibility without abandoning their position. Their counterargument was that any measurement of a red hypergiant requires a choice about what counts as the surface, and that the choice should be made where the physical properties of the star transition most sharply from stellar to circumstellar, from the object itself to the material it has thrown off. On that criterion, they argued, 900 solar radii marked the physically meaningful boundary, and the larger figure captured a region that was in transit rather than in residence. There is a further point that shaped this camp's confidence. UY Scuti, at 900 solar radii, would still be enormous. It would still comfortably reach past the orbit of Mars if placed in our Sun's location. It would still rank among the largest handful of known stars in the galaxy. The revision was not a demotion in the everyday sense. It was a correction that left the object extraordinary while removing a claim about record holder status that the researchers felt had never been well supported to begin with. That framing matters because it shows why the smaller camp position never carried the flavor of a takedown. Its supporters were not trying to strip UY Scuti of its status as a giant. They were trying to describe the star as it actually is, rather than as its most dramatic estimate suggested. And if the resulting number happened to be less impressive on the leaderboard, that was a consequence of the physics rather than a goal of the analysis. The instrument that finally forced both camps into the same room sat on a mountain in the Atacama Desert, at an altitude where the air is thin enough that infrared light passes through it with unusual clarity. It was not a single telescope, it was 4 of them, working in coordination, linked by a technique that changes what a telescope fundamentally is. The technique is called interferometry, and the facility that pushed it into the UY Scuti debate is known as the Very Large Telescope Interferometer. Its logic is worth understanding in plain terms, because the entire weight of what happened in 2012 and 2013 rests on it. When two or more telescopes observe the same object simultaneously and their light is combined with extreme precision, the resulting system behaves, in certain respects, like a single telescope whose mirror is as wide as the distance between them. Four telescopes spaced across a mountaintop can, for the purposes of measuring an object's angular size, act like one telescope hundreds of meters across. That kind of resolving power matters for a star like UY Scuti. Earlier infrared surveys had measured the star's total energy output and inferred a size from it. Interferometry did something categorically different. It attempted to resolve the star's disk directly, to measure, not the total light coming from the object, but the angular width of the object itself as seen from Earth. In principle, that removes an entire layer of assumption from the calculation. You are no longer asking how large a star must be to produce a certain brightness. You are asking how wide it actually appears in the sky. When the campaign turned its instruments on UY Scuti and processed the returning data, the size that came back was closer to the smaller camp's figure than the larger one. The star's disk, as resolved by interferometric measurement, did not match the 1700 solar radii that the earlier luminosity-based work had implied. It matched something in the neighborhood of 900, give or take a substantial margin. That result did what a decade of theoretical argument had not been able to do. It moved the smaller number from the status of an alternative reading to the status of a measurement, an actual observation of the star's apparent width, rather than an inference from its energy output. Textbooks began to add footnotes. Public-facing summaries of UY Scuti's size started to soften. What had been the star's record-holder claim quietly acquired a question mark that had not been there before. But the collision did not end the debate. It sharpened it. And to understand why, we have to look at what interferometry could not do. The first issue was pulsation. UY Scuti breathes on a cycle of roughly 740 days, expanding and contracting between phases of its rhythm. Any interferometric measurement, no matter how precise, captures the star at whatever phase it happens to be in at that moment. If the observation coincided with a contracted phase, the reported width would be smaller than the star's average size, and smaller still than its maximum reach at full expansion. The larger camp pointed to this immediately. They did not dispute the interferometric result. They disputed what the result meant, arguing that a single-phase measurement could not settle a size that varies substantially across a 2-year cycle. The second issue was distance. Every size derived from an angular measurement depends on knowing how far away the object sits. Angular width is a proportion. It tells you how large the star appears in the sky, and that appearance has to be multiplied by distance to yield a physical radius. UY Scuti's distance, at roughly 10,000 light-years, carries a margin of error large enough that even a small shift in the assumed value moves the size estimate by hundreds of solar radii in either direction. The interferometric campaign used the best distance estimate available at the time. That estimate, however, was not itself a direct measurement. It was inferred from other properties of the star and its surroundings, which meant that any correction to the distance in future work would automatically ripple back into the size. The third issue, and perhaps the deepest one, involved what the interferometric measurement was actually resolving. Interferometry captures the boundary at which the star's brightness drops off sharply enough for the instrument to register an edge. That boundary is real, but it is defined by the same wavelength dependence that had shaped the debate to begin with. The interferometer was working at a specific set of infrared wavelengths, and those wavelengths reach a specific depth inside UY Scuti's fuzzy outer atmosphere. A different interferometer, working at different wavelengths, might resolve a different edge, hundreds of solar radii away. Both camps saw this. Both camps drew different conclusions from it. The smaller camp researchers argued that the interferometric result had captured the physically meaningful surface, the place where the star's density and temperature transition sharply enough that any reasonable definition of an edge lives near that boundary. The larger camp researchers argued that the result had captured one of several possible edges, and that the star's true extent, as defined by luminosity, still favored a substantially larger figure. Neither side conceded. And that is the honest shape of the collision. The interferometric campaign did not deliver a verdict that either camp was compelled to accept. It delivered a data point, a very good one, arguably the best single measurement UY Scuti had ever received, that constrained the debate without ending it. The smaller number gained a direct observational anchor it had not previously enjoyed. The larger number lost some of its unchallenged position in the textbooks. What emerged from the mountain in the Atacama was not a resolution. It was a genuine tightening of the disagreement. More than a decade has passed since the campaign on the Atacama returned its result, and the shape of the disagreement now is not the shape it wore in the years immediately after. Both camps have refined their positions. Both have absorbed new data. Neither has surrendered. What the larger camp still has is a physics-based argument that has never been dislodged on its own terms. The luminosity of UY Scuti, its total energy output across every wavelength that has been measured, remains extraordinary. The dust envelope that surrounds the star, stretching outward to roughly 400 times the distance between Earth and our Sun, still exists. It still had to come from somewhere, and it still points backward toward a source large enough and active enough to have produced it over hundreds of thousands of years of mass loss. Their argument, refined in the years after the interferometric campaign, has become less about defending a single number and more about defending a category. Even if the star's apparent width at certain wavelengths comes in near 900 solar radii, the physical extent of the object, everything gravitationally connected to it, everything participating in its energy output, everything that is still meaningfully part of the star rather than of the surrounding interstellar medium, reaches much farther. In this reading, the interferometric measurement captured a boundary that is real but not exhaustive. The star has a core body of one size and an extended envelope of another, and both, in their view, deserve to be counted when the question is asked in its most physically honest form. There is also a genuine appeal to caution built into this camp's ongoing position. Interferometric campaigns, however precise, sample the star at a single moment in its pulsation cycle. If you want to know how large UY Scuti actually is on average, across its full expansion and contraction, you need many measurements taken across many phases, and that campaign has not yet been fully carried out. Until it is, the larger camp argues, the smaller number should be treated as one piece of evidence among several rather than as a settled answer. Their position is not that the interferometric result is wrong. It is that the interferometric result is incomplete, and that a star whose radius varies substantially over a 2-year cycle cannot be reduced to a single figure without qualification. What the smaller camp still has is the observational anchor that its position acquired on the mountain, and a set of physical arguments that have only grown stronger in the years since. Stellar evolution models continue to struggle with the idea of a stable object at 1700 solar radii. Mass loss rates observed at that scale would strip the star of its outer material faster than the star could sustain itself in that configuration. Refinements in modeling have narrowed rather than widened the range of radii that a red hypergiant of UY Scuti's estimated mass can plausibly occupy, and the smaller figure sits much closer to the middle of that range than the larger one does. The smaller camp has also gained ground on the interpretation question. When interferometry finds a sharp drop-off in brightness at a particular boundary, that boundary corresponds to a real transition in the star's physical structure. It is where the gas density falls off steeply enough that light can escape freely rather than being scattered by material above it. That transition, on any reasonable definition of what a star is, has a strong claim to being called the star's surface. The camp's argument is that the larger radius describes something else, a region that is still glowing, still connected to the star, but no longer part of the object in the sense that a stellar surface is usually understood to be. What has changed for both camps is the surrounding landscape. UY Scuti is no longer being measured alone. The same techniques that shrank its accepted radius have been applied to other red hypergiants, and the results have complicated the leaderboard in ways that neither camp anticipated. Stevenson, 218, sitting even deeper inside the galaxy, has produced size estimates that under some interpretations exceed even the larger figure for UY Scuti. Under other interpretations, it barely competes. Canis Majoris, one of the most studied hypergiants of the last several decades, offers a size range wide enough to overlap with either UY Scuti figure depending on which method you trust. Wo G64, sitting in a companion galaxy roughly 160,000 light-years away, is enormous by any measure, but similarly resistant to a clean number. The competition among these objects has not resolved. It has multiplied. And that has changed the emotional stakes of the UY Scuti debate in a way that is worth naming. When the question was whether UY Scuti held the title of largest known star, both camps had a strong incentive to defend their number. Now that several stars compete for that title, and none of them offer measurements clean enough to settle the ranking, the fight over UY Scuti's radius has become part of a larger question about whether the category of largest known star is coherent at all. That larger question is where the honest state of play now lives. Every one of these hypergiants has fuzzy outer layers. Every one carries a dust envelope. Every one pulses. Every one sits at a distance uncertain enough to affect the size calculations substantially. If you demand a single number that describes the physical extent of any one of them, you will get answers that depend heavily on which definition of extent you accept, which wavelength you observe in, and which phase of the pulsation you catch. That is not a failure of astronomy. It is what stellar physics looks like when it runs up against objects whose defining property is that they do not have clean edges. There is one further point that both camps have quietly converged on, and it is worth putting in the open. The mass loss that UY Scuti is undergoing, the constant stellar wind pouring material off its outer layers, the pulsations that pump gas outward with every cycle, is not slowing down. Whatever the star's current radius, its future radius will be smaller. It is losing itself in real time, and the fraction of its original mass that now sits in the surrounding envelope is substantial enough that the star we measure today is already a diminished version of the object it once was. That has implications for how the debate will eventually be settled, if it settles at all. Future interferometric campaigns, using instruments more powerful than those that operated in the early 2000s, will measure UY Scuti at multiple pulsation phases and refine the star's average radius rather than its snapshot radius. Refined distance measurements, using techniques that were not available when the current numbers were locked in, may shift the calculated size again, possibly toward the smaller camp's figure, possibly toward the larger camp's, possibly toward a middle ground neither camp currently occupies. Continued monitoring of the star's dimming behavior, of its color shifts, of its mass loss rate, will fill in the picture of what UY Scuti is actually doing right now, which will in turn constrain the physical models that both camps rely on. The question of whether the star will end in a supernova, and when, remains genuinely open. Red hypergiants can collapse without warning, or they can spend hundreds of thousands of years on the edge of collapse before finally letting go. If UY Scuti detonates within a human lifespan, the resulting observations would settle a great many questions about the object's mass, its structure, and by extension, its radius. If it continues to breathe for another 100,000 years, the debate we are describing will continue to breathe with it. So the question we started with, whether UY Scuti is the largest known star, or whether it has been overtaken, does not have an answer today. Both figures live. Both are defended by researchers who have looked closely at the same object and come away with genuinely different, genuinely defensible